In the last class, we have formulated the principle of WKB and have seen the criteria for the validity of WKB method. Now in this class, we will consider a general expression for the WKB wave function that will help us to write the wave function representing the problem under our choice depending upon some standard parameters associated with the particular problem. We have already stated that WKB is an approximation method suitable for stationary problems or time-independent problems. So that in considering a general expression for WKB wave function, we will of course limit our discussion in the regime of stationary problems. As you know, or as you have developed from quantum dynamics, in the case of stationary problems, the wave function can be taken as the product of a space-only dependent part, which is being represented as a phi of r here, and a time-only dependent part, which is being represented as a chi of t, where this time-only dependent part will generally have a format in terms of the energy eigenvalue E as, say, exponential minus I by h cross energy into time. And in the regime of WKB method, we will be then interested in this space-only dependent part, because WKB is a method suitable for stationary problems, and hence we are interested in the space-only part of this wave function. And if you are interested in writing the entire wave function representing the system at any instant of time, you just require to multiply the space-only dependent term by means of the general expression for the time-only dependent term. So it is this part of the wave function in which we are interested. And of course, phi of r will generally have a formulation in terms of the space-only dependent part of the action, as we have seen while we talked about the principle of WKB method, which is a W of r, or which for the time being I'll be representing it as a W of r. So phi of r will have a general formulation exponential I by h cross W of r, such that the total action representing the semi-classical system may be written as S of r comma t equal to W of r minus energy into time. This also gives an illustration of the separable nature of the space-only dependent part and time-only dependent part of the stationary quantum states. So clearly W of r is the space-only dependent part of action, and energy into time represent the time-only dependent part of the action. I will not be specifying it as a classical action or quantum mechanical action. If we are writing an expression on the basis of the classical equation of motion, generally we will be taking this as classical action that will have only one constant component, which we have already represented as, say, S0. Corresponding to such a classical action devoid of any component in terms of the exponential series, in terms of the different powers of h cross, there will be only one constant space-only dependent part for this classical action that I will be representing W0 in the subsequent discussion. And if we are making a comparison with a quantum mechanical system for the real system, then the action will be represented as, say, S. And from the principle of WKB that we have just formulated, we have seen that this action will have so many steps, or this is most suitably represented by means of a series expansion in terms of different powers of h cross. And in the limit of WKB method, we will be contented with the first two terms, S0, a constant part, plus h cross by I, that is the term containing h cross as long as the semi-classical approximation is concerned. H cross by I is 1, where S1 is the first coefficient of the first power of h cross, or the term having h cross with a power 1, because this term will have h cross having a power say 0. So corresponding to S0 and S1, there will be two different parts for the space only dependent part of action W, that I will be representing as a W0 plus h cross by I W1. That also goes with this general expression for the total action. So now we will be interested in identifying W of R, so that we will be able to write the wave function, that is WKB wave function, in the format phi of R equal to e raised to I by h cross W of R. So the problem has now decomposed into the problem of identifying W of R in the semi-classical limit, or in the limit of the WKB approximation. So that simply by putting W of R in this expression, we will be able to identify the general expression for WKB wave function. Clearly, I have mentioned you W of R will be equal to W0 plus h cross by I W1, h cross by I W1. So now our problem involved the evaluation of W0 and W1, so that we can write W equal to W0 plus h cross by I W1, substitute that value of WR in this general expression. That will give us a formulation, or a general formulation of the WKB wave function. Of course, then for that the mode of operation will be, first of all, the evaluation of W0 and then the evaluation of W1. Where shall we get these parameters W0 and W1? Of course, we can have them from the corresponding differential equations in W0 and W1. That equations could be obtained from the classical equation of motion that we have written in terms of action, and the quantum mechanical equation of motion that also we have written in terms of action. While we talked about the principle of WKB, the classical equation of motion is given by minus dou s by dou t equal to grad s whole square by 2 mu plus v, where s is the classical action. Better I might have represented this as say S0, but earlier I have represented it in terms of S only, and it was stated that it is the classical action. Here also I will be using the same representation, such that S in this equation represent the classical action, and in the subsequent equation the same symbol will be used to represent the semi-classical action, or action within the regime of the validity of WKB method. Now we substitute S equal to W0 minus ET as long as this equation is concerned. Clearly minus dou S by dou T will be equal to, this part is space only dependent, it has no significance as long as a differentiation in time is concerned. So that derivative of S with respect to time is minus E. So minus dou S by dou T is equal to plus E. And grad S will be, grad as you know is a space only dependent differential operator. And again we will be limiting WKB, or we have already seen that WKB will be generally applied in the case of one-dimensional problems, or problems that could be decomposed into the sum of one or more than one-dimensional problems. So here also in this general formulation I will be considering WKB in one dimension, that's along the x direction. So grad S has the meaning of d by dx. So grad S in this case will be dw0 divided by dx. Substitute these values of minus dou S by dou T and grad S in this expression, we will get a homogeneous differential equation in W0 the classical part of the space only dependent part of the action, and this is given by E equal to, we have substituted minus dou s by dou t equal to E equal to 1 by 2 mu grad s whole square. Instead of grad s, I'll have dw0 by dx whole square plus V. For writing it in the format of a homogeneous differential equation, for that you'll have to multiply the entire equation by 2 mu and take the term 2 mu into E from left side to the right side, and the first term will be then appearing as dw0 by dx whole square plus 2 mu into E from the left side being fetched to the right side become minus 2 mu into E, and already I have plus 2 mu into V on the right side. I have taken a minus out to make it say minus 2 mu into E minus V of x equal to 0. Take care of this quantity 2 mu into E minus V. This will have a particular representation. I'll tell you it very shortly. For the time being, it is E minus V is the total energy and V is the potential energy. So E minus V is definitely total energy minus potential energy, and for the WKB system we have taken the total energy to be the sum of the potential energy and kinetic energy. So the quantity in this bracket is nothing other than the kinetic energy, and I am multiplying kinetic energy by means of 2 mu, which is nothing other than the momentum possessed by the classical particle or the classical momentum. So this equation will be my implication for the solution towards a W0, and I require W1 also, so that I will be able to take the total space only dependent part of the action possessed by the WKB system. Then I'll have to find another equation for W1. This of course we can obtain from the quantum mechanical counterpart of the classical equation that we have already seen. The quantum mechanical equation is minus dou s by dou t. Here S is the quantum mechanical action or the total action. I must tell it the total action, and once I put this to be equal to say accuracy to the first two terms, then definitely this will be the action within the limit of the validity of WKB method. So the quantum mechanical equation is minus dou s by dou t equal to grad s whole square by 2 mu plus V minus IH cross by 2 mu del square S. Here S is clearly W of R minus ET with W equal to this series expansion or being represented by this series expansion. So we substitute these values of minus dou s by dou t, say grad s and del square s. Here also minus dou s by dou t equal to space derivative of this s, that's equal to E. Grad s is nothing other than dw by dx. Take care of this quantity. W is not simply a single term, it contains a series expansion. So we substitute here minus dou s by dou t equal to E. 1 by 2 mu is written here. D grad s is nothing other than dw by dx. So we substitute it dw by dx whole square plus V minus IH cross by 2 mu. Del square S is nothing other than del dot grad s. Del dot grad s will be then the second derivative of W with respect to x. This equation also we write in a standard format. For that we take we multiply the entire equation by 2 mu and take the quantity from the left side to the right side. Then this becomes 2 mu into this quantity, 2 mu vanishes, dw by dx whole square plus 2 mu into E from left side is taken to the right side to make it say minus 2 mu into E. Already on the right side we have 2 mu into V. 2 mu here in this term, third term also vanishes to make it say minus IH cross d square W by dx square, and I have forgotten to put or equate this to say 0. Now we rearrange them. dw by dx whole square minus 2 mu is taken as a common factor from these two quantities. This also converts to momentum of the particle, minus 2 mu into E minus V minus IH cross d square W by dx square. And the Schrodinger equation, IH cross dou psi by dou t equal to minus h bar square by 2 mu del square plus V operating over psi